If the series limit wavelength of Lyman series for the hydrogen atom is 912 angstroms, then the series limit wavelength for Balmer series of hydrogen atoms is to be calculated. If we have an hydrogen atom, what is the force that is keeping the electron in orbit around the atom? The centripetal force must be equal to mv squared by r. And the only force that can fulfill this role is the electrostatic force, which is kq1q2 by r squared, where q1 and q2 are the charges of the electron and the proton. Now, a moving electron would have a de Broglie wavelength associated with it due to particle wave duality. And that de Broglie wavelength is given as lambda b is equal to h, which is a Planck's constant, divided by mv, which is the momentum of the electron. And in the Bohr model, an orbit, a stable orbit, can only be formed if the length of the orbit, that is 2 pi r, is an integral multiple of the de Broglie wavelength. Now, combining all these three conditions, if we try to calculate the total energy of an electron by comparing or adding the potential energy, which is minus k q1 q2 by r, and its kinetic energy, which is 1 by 2 mv squared, we would find out that this is proportional to 1 by n squared. Therefore, as n tends to infinity, we would have energy to be equal to 0. That is, a free electron has no energy. Now, what are Lyman series, Balmer series? Lyman series is any transition between n is equal to 1 to any other higher n value. Balmer series is any transition between n is equal to 2 to any higher n value. The transition between n is equal to 1 and n is equal to 2 would lie in the Lyman series because that is a lower value. Now, what is a wavelength limit or limit wavelength? A Lyman series has transitions from n is equal to 1 to n is equal to 2, n is equal to 1 to n is equal to 3, to n is equal to 4, n is equal to 5, and so on, and it never stops. But as it tends to infinity, the energy difference between the two states would approach a limit. And what is that limit? We have energy of n is equal to 1 minus energy of n is equal to infinity. The magnitude of this is given to be hc by lambda, which is the wavelength of the photon associated with this transfer, and this lambda is equal to 912 angstroms. But since we know that E infinity is 0, this only tells us that the energy of n is equal to 1 is associated with the wavelength of 912 angstroms. Similarly, the series limit wavelength for Balmer series would also be equal to E2 minus E infinity, but since E infinity is 0, this would simply be E2. Now we are given that the energy is proportional to 1 by n square. So if E1 has some energy, the energy of E2 would be 1/4 of that. Therefore, this would be equal to E1 by 4, or hc by 4 lambda. Therefore, we can determine that the required wavelength, which is the series limit for the Balmer series, would be equal to 4 times 912 angstroms. And hence option C is the answer.